next speaker is Jonathan Rudd. Jonathan is President of DS Geophysical Limited, an IP and resistivity service and technology provider. Jonathan graduated from the Geological Engineering program at Queen's University with a specialisation in geophysics. Jonathan has worked primarily in the mineral exploration industry and has been involved with airborne and ground contractors and consulting firms.
Thanks, Brendan. Appreciate the opportunity to speak today. I apologize for my voice. I've been suffering from a bit of a cough. Hopefully it's not too much of a distraction. This talk was originally planned to have another company involved, but the permission process was fairly extrapolated, so I've had to pull a lot of the perhaps more interesting integration aspects of the talk out. So hopefully you'll be sufficiently engaged so that you don't fall asleep during prime nap time here. My co-authors on this talk are Scott Napier of Mira Geoscience and Glen Chubak, who's our VP Technology at DS Geophysical. So today I'm going to talk about a bit of the background of the survey that we completed, talk about the survey itself, the processing and modeling that we did with the data, show some results, and then draw some conclusions. So we completed a 3D resistivity survey in an application where we're trying to map and characterize aquifers and to understand sort of controls on the groundwater through the survey area. We surveyed a relatively small block. That orangish square is 500 meters by 500 meters. It's in the middle of a farm field. And the idea was to map down to a depth of over 120 meters with the resistivity parameter, but also get some high resolution information in the near surface. And the reason for that is because we need to understand the interaction between the water that's entering the system from rain or snow or whatever in the spring and the aquifers that are there already. So we needed to achieve a resolution of 2.5 meters in the near surface, and then increased resolution to that depth of about 150 meters. The geology in the area is pretty complex. It's typical of the middle provinces of Canada. Till, sand, gravel, silt layers overlying Cretaceous bedrock. In this case, it's a shale bedrock. There's a lot of paleo channels through the area. These can be anything from very small channels to quite large and extensive channels. In this particular application, the interest was in mapping a deep aquifer, but also understanding what interaction there is with the shallower aquifers through the survey area. Typical resistivities that we expected in this survey were 5 to 10 ohm meters, so fairly conductive for the finer material. Sand and gravel was 50 to 100 ohm meters, and the till lies in between, so there's a bit of overlap in the physical properties of the geology in the area. And the shale bedrock is quite conductive at around 5 ohm meters. So the survey was done as in 2 stages. The first stage was to do a coarse scale. This was to achieve the depth of exploration that they wanted to over 100 meters. So we laid out 64 receivers. Those are the green dots, 8 by 8 at a 70 meter dipole spacing, 70 meter electrode spacing. And we injected 257 times. You can see corner shots just to fill in the information at depth underneath. So overall, we were acquiring about 16,000 pole data records, and I'll talk a little bit about the survey methodology later. And I think the modeling was done at 20 to 25 meter resolution of this data set. The second phase of the project was a fine scale survey. So this is exactly the same layout of receivers and injection points. We used a 7-meter electrode spacing for this. And this was basically in the northeast corner of the coarser scale survey. The idea of this is to just get that added resolution in the very near surface. The DS32 system, this is our receiver. It's about 16 centimeters long, I guess, by 9 by 5 or something. Single channel receivers, how we use them, deploy them, is we install receiver electrodes, or voltage electrodes, and then we put a receiver box at each electrode. And then these can be laid out really in any fashion, whether random or a regular grid. And then we just connect them with a single voltage reference wire. And then we inject our current through the survey area in whatever pattern makes sense for the application. Each receiver is, as I mentioned, single channel. It requires time series data. It has a good about a week of battery life, and it has GPS positioning and synchronization. How do we set up with respect to the wiring? I mentioned the concept of a single reference wire. Here we have a single reference wire grid for the receiver electrodes. So we lay out wires along each line and then hook them all up to make it a single common voltage reference. And then we lay out our electrodes and receivers along those lines. And then we inject using a non-intersecting current transmission grid. And then corners. We also collect 2 sets of data when we do this style of survey. So we're collecting pole dipoles, so our current injection is a pole. We have a remote electrode for that, and then we are measuring pole information within the survey area. But if we put a remote electrode out for the voltage as well, we can then derive both pole dipole and pole data from the same data set, so simultaneously. And there's advantages to this, obviously, in the fact that you have the added depth sensitivity of the pole data set, and a little more flexibility in how you invert your data. When we do our survey design, we can take a look, sort of similar to what was just discussed with the seismic survey. We can look at bins. It's not exactly the same, obviously, it's a different method, but we can think about it that way. So each of these cells or bins represents the current distribution that's flowing through at the assumed depth. We're assigning a certain depth for each of these things. So you can see that in the near surface, wrong button. You see in the near surface here, the resolution or the bins have lower resolution, and then at a greater depth, at about an N of 2 to 3, you're starting to get your highest density of information. So your resolution of the survey actually is lower than in the very near surface, increases, and then it drops off to greater depth. And then likewise, laterally, your greatest resolution, of course, is in the center of the survey area and falls off to the edge. You can see the electrode and shot point locations in the background. We do a similar, we depict the directionality, I guess, or the orientation or the azimuth of the transmitter receiver using a rose diagram. And this just represents the directionality of this particular survey. And you can see here in the top 70 meters, we do have a bit of a bias in the direction of the receiver and transmitter dipoles. In middle depths, it's a very sort of even directionality. And then at great depth, you can see the effects of the corners of the survey area, northwest to southeast and northeast to southwest. A good way to sort of understand how well your survey design is planned for 3D information. How did we process and image this data? Obviously, you're picking your code. There are a number of 3D codes for doing 3D inversion of resistivity and IP data. We have to, the process of determining the input data is actually not trivial. There's an awful lot of data, both dipole and pole-pole. You have to remove your ill-coupled dipoles or null-coupled dipoles for your pole-dipole data set, and you have to look at the data quality for both. And then make the decision on whether you're going to do a joint inversion or invert independently. Determining the inversion parameters as well. Each area is quite different in terms of what parameters are most optimal for the model. And deciding on a starting model can be a challenge as well, as we've seen today. We complete a sensitivity analysis as well, and that's not an overly trivial process. We have to, in this case, we have to reduce the sensitivity compression threshold. Run times for this data set, considering both pole-pole and pole-dipole data, I think there was about 40 to 50,000 data points, were for 6 to 8 hours on a relatively modest desktop computer. And the thought is that the relatively high transmitter to receiver ratio, or receiver to transmitter ratio, fit into this. So the ability to measure pole-pole data allows you to QC that data set quite easily. Here we see a view of the measured pole information from each receiver for a single injection point. Here's your injection point, and you can see the voltage falling across. In this case, this particular pole is obviously erroneous. It happened to be connected in reverse, so it was fixed in the data and processing. But we have this view live, so we can be viewing this data as a QC tool as we're collecting, as we're doing our surveys. How do we extract dipoles? We're just measuring time series for each individual electrode against the common voltage reference. Well, you can then extract as many dipoles or as few as you want. You can pick any two electrodes and subtract them, and you generate a dipole. So here's an example of two electrodes. EH and FN are the two nodes, and you subtract the two and you end up with the result. So you can see some relatively long period noise running through the data set. You can see when you subtract, that noise cancels out. So it's one of the advantages of the common voltage reference is that any noise in that wire, the common voltage wire, will entirely cancel out. Even at the high frequencies, there's the same data set, same two nodes, a single half wave. And you can see there's noise, high frequency noise in both of the individual node responses, and the subtraction is a much cleaner data set. The flexibility of how to build your nodes and cull them is not a trivial problem either. In this case, we built dipoles across each cell of electrodes, and we built dipoles on the sides of each cell as well. So a large number of dipoles, and then we run an automated method to determine what is null coupled or minimum coupled to the current injection point. So in this case, we've assumed estimated what our positional error is, and then we convert that to a resistivity error, and then we just select a rejection threshold for that. And in this case, you can see all these red dipoles have been rejected because this nulling factor was exceeded. So with the high volume of data, automated processes are almost required here. So 49,950 data points, that's both the pole and pole-dipole data sets, came out of that nulling process. And these data were further reduced to about 47,000 through some other QC parameters, visual, identifying and removing visual outliers, inversion outliers as well. And it's about 6% of the data set. So on the left we can see a point cloud, and you can see some potential data outliers that just don't make sense. And likewise, this is the inversion. It's a normalized voltage difference of the predicted and the observed results. Data fit and the model sensitivity. We selected a variety of reference models. Here we see on that we've used a different half-space reference models at 20 millimeters, 13, 7.5, and they're represented here. And you can see that in the near surface, all of those reference models work quite well. As you get to greater depth, you can start to see deviation away. In general, we got an excellent data fit with a mean of 1.2% through the whole data set. We had access to some well logs. In this case, it was a single point resistivity log, uncalibrated. This is the model in the vicinity of that well. And if I just overlay a trace of that, I've arbitrarily scaled that uncalibrated SPR log to generally match the geology here. But you can see that there is in the near surface a fair difference between. If you look at the depth, really the top, this is your dipole spacing, 0 to 70. So you could expect there might be some variation in the very near surface because you just don't have that resolution. This is the coarser data set. But at depth, you can see that the two actually match quite well. So here's a 3D resistivity model image from the inversion process. You can see that it's mapping near surface and aquifers at depth. And there is a barrier in between them. Understanding that barrier is pretty critical to the survey here. So this is the deeper aquifer. We've outlined it as anything greater than 20 ohm meters and at a depth of greater than 480 meters, or less than 480 meters. And you can see that the aquifer is thickness and continuity varies through this 500 meter by 500 meter survey walk. So if you take that aquifer and sort of isolate it out and look at it in plan view, we can see that the lateral variation is pretty significant. There seems to be a big change in the character of that aquifer at that depth, at that location. On the southeast side, it's well developed in the resistivity model, quite thick and consistent. But as you go to the northwest of that boundary line, it's a much thinner and less certain. In fact, there are holes in it, and the drilling has confirmed that changing character. The fine scale survey was inverted with the Loke code, and you can see just a single set of results here. These are sections across that fine scale block. Again, 7 meter electrode spacings. So 7 sections, and you can see a relatively well developed aquifer in very near surface, about 5 meters depth, 4 to 5 meters depth, consistent all the way up through until you get to the northern section. It starts to fade out a little bit. So The resolution of our fine-scale survey was found to be sufficient for mapping the near-surface features in greater detail. The resolution of the coarse-scale data set is sufficient to map the larger-scale features, but falls down in understanding the details of these aquifers, which can be important to the I guess, hydrology in the area. A combined coarse and fine-scale survey really is the ideal solution for this survey area. But the reality is doing that is an extremely challenging proposition, because it would require thousands and tens of thousands of receivers, which we just don't have available. They're available in the seismic industry. They're there. We're not there yet. So we're taking a look at how we can achieve those objectives with our equipment limitations. Analysis of the chargeability data, a little bit more complex. We have chargeability inversions, and it's not as clear geologically as the resistivity parameter. So we're proposing a 3D solution. It's actually a dual resolution survey using a 50-meter inter-electrode receiver spacing and a 5-meter inter-electrode receiver spacing. So that would look something like this. There's your coarse grid. These are at 50-meter spacings across the survey area, and then you can go in and fill in a much finer portion of the survey area, inject, and then move along as you're injecting through the survey area. So in this way, your the area in and around your transmitter injection point is well populated by receivers. That's where you need your resolution, and then you've got a good, nice, wider spacing electrodes that are more distal. So you're guaranteed a better signal, and you don't really need the resolution in those more larger offset transmitter-receiver separations. So this is going slow, but this type of survey would go slow, I guess. And so the rest goes fast. So fairly involved survey. It would be time-consuming and require a fair number of people. But to meet the objectives of this project, it would be our recommended way for doing that. You can really decide what fine resolution you want, depending on what resolution you need in the near surface. So you could do this at maybe a 200-meter coarse grid separation and a 100-meter fine, 250, depending on what you want to achieve in terms of the resolution across the survey area. All can be done with this common voltage reference style of survey. So we found that the 3D resistivity is adding value to the mapping and characterizing of aquifers in this area. The vertical resolution is not enough to accurately map the details in the deeper aquifers, but it's doing a good job in generally mapping those aquifers. In some cases, it's difficult to distinguish between till and aquifers because of the lack of conductivity contrast. And the dual resolution surveying is a requirement for this style of application. That's it. Thank you.
We've got time for some questions.
Jonathan? What was the purpose of the current flow directionality study?
I think it's really important to understand how 3D a 3D survey is. And if you don't have current flowing in all directions, you don't really have a 3D survey. So you look at an offset 2D survey. If your electrodes are all running along a couple lines, you have very, very little 3D information. So I think the rose diagram is a very good way of depicting that, particularly to geologists who understand those types of diagrams, and it can help us as well to understand how well we've designed our surveys for the purpose.
Doug?
A couple of questions. First of all, I really enjoyed your talk. My question is, you paid a lot of emphasis to getting rid of non-coupled primary data. What was the purpose for that?
So where your dipole is running along a voltage equipotential, you have extremely high error in your resistivity calculation, or voltage, depending on what you're using. So as a result, those readings are unreliable and should not be used in the inversion process.
Because if, I mean, when you can think about things that are potentially null coupled, but your three-dimensional conductivity structure will actually provide some signal. And just so long as you assign responsible uncertainty for the data error, which is much more geared to what error your base level is, I don't see any problem with those null coupled data. They
Yeah,
actually might
if you-
provide
I think
a lot
if
of
you-
information.
Yeah, no, I agree. There is value in understanding how those, how your current is, warping and whatever it does. However, if you've got a resistivity value with 1,000% error, it really is not adding anything to the picture.
Okay, good, maybe fair enough.
Yeah.
My second question is, with your new system, you can actually sample quite rapidly. Is that true? In other words, can you get the early time channels after you switched off so that you might consider using your data in a time domain EM system?
Yeah, I mean, we're sampling. Right now, we're limited. Our focus is on IP resistivity survey, so our sampling rate is at between 200 and 300 samples per second, but we're going to be upping that shortly. But no, there's nothing to stop the system from being used to record EM data or whatever. It's just a matter of the sensors.
Peter?
You said your aquifers are more resistive. That's unexpected for me. So what's the situation? Is you've got till, it's very clay rich, is it?
Yeah, it's really the clay content that drives your conductivity. There's very little. I mean, there are some areas where you get brines and saline water, but in general, in this area, it's pretty fresh.
Peter?
There seems to be quite a market developing in Europe for IP being used to map contaminant plumes and old slag heaps and things like that. What I noticed is that they are using control parameters or sort of the frequency content of IP. So it becomes important to sample the decay waveform quite well over a long time. And I think your system could be adapted to that. So,
Yeah, I mean, we're committed to measuring the time series, and we are well on our way to increasing our time, our sort of sampling rates. And there's several groups that are demanding a much higher sampling rate, even on the IP side. Yeah, the resistivity side. Yeah.
Well, thank you again, Jonathan.